Section 5.2, bisectors in a triangle. First, Theorem 5.2, perpendicular bisector theorem. Let's first recall what a perpendicular bisector is. If I'm given a segment AB, and I have a line N that I know is a perpendicular bisector to AB, then we know that line N is perpendicular to AB, and that it bisects it. That means it intersects at the midpoint of AB. Therefore, we know that segment AM is congruent to segment MB. Here the theorem states, if a point on the perpendicular bisector of a segment, then the point is equidistant to the endpoints of the segment. So if I would place a point on the perpendicular bisector, we could call it any point. Here I can label that as C. Then I know that the distance from that point to the endpoints of the segment are going to be congruent. And I know that I can slide point C in any direction as long as it stays on line N, which is the perpendicular bisector. I also could place point C below segment AB, and I still would know that the segments are congruent, or that point C is equidistant to the endpoints of the given segment. Theorem 5.2 is the perpendicular bisector theorem. Theorem 5.3 is the converse of that perpendicular bisector theorem. Therefore, 5.2 is if P then Q. This would be if Q then P. If a point is equidistant to the endpoints of a segment, then the point must lie in the perpendicular bisector of the segment. Let's look at a proof to verify Theorem 5.2. Here I'm given that AD is perpendicular to BC. So, step 2, I can state that segment AD is perpendicular to BC. Therefore, I know that angle ADB is congruent to angle ADC. And that would be because perpendicular lines form congruent adjacent angles. Step 3, I'm given that AD bisects BC. Therefore, I know that point D is the midpoint of BC, and I can state that BD is congruent to DC. And that could be because of definition of segment bisector. I also could say definition of midpoint. Now, my goal is to get triangle ADB congruent to triangle ADC, and from previous sections, then I can use CPCTC to get what I need to prove congruent, which is that segment AB is congruent to segment AC. So, I have two parts of the triangle already congruent. I need a third part. I can use AD congruent to itself, segment AD, because of the reflexive property. Now, I know the triangle ADB is congruent to triangle ADC. And the reason for that is side, angle, side. Step 6 is segment AB is congruent to segment AC because of CP, CT, C. And that proves that a given point on the perpendicular bisector, and the given tells us that AD is the perpendicular bisector of BC, and that given point A is equidistant to the endpoints of the segment. On this slide, we're asked to use the figure to complete the questions. Number 1, name the perpendicular bisector. Here I have triangle ABC. In the diagram, I know that AD is perpendicular to BC, and that point D is the midpoint of BC because it's shown by tick marks that BD is congruent to DC. Therefore, segment AD is the perpendicular bisector. Number 2, name two pair of congruent segments. The diagram already demonstrates one of them, and that is that segment BD is congruent to segment DC. But point A is on the perpendicular bisector, which we already named in number 1. Therefore, point A is equidistant to the endpoints of the segment, which are B and C. That tells me that segment AB is congruent to segment AC. Number 3, name a pair of congruent angles. Actually, we can name two of them. We know that here, if I label angle 1 and 2, angle 1 is congruent to angle 2 because we know that perpendicular lines form congruent adjacent angles. I also know that segment AB is congruent to segment AC. Therefore, this is an isosceles triangle. And by the isosceles triangle theorem, if two sides of a triangle are congruent, then the angles opposite must be congruent. Therefore, angle B is congruent to angle C. Number 4, if point K is on the perpendicular bisector of BC. We don't have a point K, therefore I can put point K anywhere on this perpendicular bisector. And if I put a point K on the perpendicular bisector, then I know it is equidistant from point B and D, or that tells me that AB is the same length as AC. On this slide, we're given that segment AH is the perpendicular bisector of segment DE, CF, and BG. Therefore, AH is perpendicular to each of those segments. And it's bisecting each segment. Therefore, BI is congruent to IG, CJ is congruent to JF, and DM is congruent to ME. They want us to find the length of AB. If AI, which is part of AH, is a perpendicular bisector, then A is equidistant to the endpoints of that segment, which are G and B. Therefore, AG is congruent to AB. If AG is 3, then AB must be 3. They want us to find the length of AC. AJ is on the perpendicular bisector. Therefore, A is on that perpendicular bisector. Therefore, it is equidistant to F and C. The length of AF is 8, 3 plus 5. And AF is congruent to AC. Therefore, AC must be 8. JF. JF is congruent to JC. So JF must be 3. IG. IG is congruent to IB. IB is 1, therefore IG is 1. BC. BC is going to be congruent to JF. I know that because AF is congruent to AC, and AG is congruent to AB. If these two segments are congruent, then these two segments must be congruent. Therefore, BC must be 5. Next, they want us to determine that segment DH is congruent to segment HE. And even though that segment is not drawn in, we know that is to be true because if H is on the perpendicular bisector, then it's equidistant to the endpoints of the segment. Next, angle ACJ. ACJ must be congruent to angle AFJ. And that is true because we know that AC must be congruent to AF. And by the isosceles triangle theorem, if two sides of a triangle are congruent, then the angles opposite must be congruent. Our next theorem, 5.4, angle bisector theorem. If a point is on the bisector of an angle, so I can quickly create an angle. I can label it A, C, and B. And we are having an angle bisector, so I'll create an angle bisector. And I have a point on the angle bisector. I can call that point K. And the theorem states if a point is on the bisector of an angle, then that point is equidistant to the sides of the angle. But we have to keep in mind that the distance from a point to a line is the length of a perpendicular segment from the point to the line. Therefore, I have to determine a segment that is a right angle to each side of the angle. Then, this length, which I can call X, and this length, which I can call Y, would be congruent. In other words, if I have a point on the perpendicular bisector of an angle, then the segment that is a perpendicular segment from that point to the sides are congruent. Therefore, I know that KA is congruent to segment KB. And that means that the length, which is X, and the length, which is Y, would also be equal. Theorem 5.5, the converse. On theorem 5.4, we stated the angle bisector theorem, which is written in the form of if P then Q. The converse is written in the form of if Q then P. Therefore, if I have a point that is in the interior of an angle, then that point is equidistant from the sides of the angle if that point lies on the angle bisector. Let's verify theorem 5.4 with this proof. Here we're given that angle DAC is congruent to angle BAC. And I can put my arcs in here. That's going to let me know that segment AC must be an angle bisector because it's dividing the angle DAB into two congruent angles. I'm also given that CD is perpendicular to AD and CB is perpendicular to AB. And they want me to prove that segment CD is congruent to segment CB. I now have two angles that I know to be congruent in each triangle. Here the right angles we know are congruent, and in the given, we're given that angle DAC is congruent to BAC. Now all I need to do is to get a third part of the triangle congruent, and I can do that by AC congruent to segment AC, and that is because of the reflexive property. With that information, I can get two triangles congruent. That would be triangle BAC congruent to triangle DAC. And the reason would be angle, angle, side. Step 4. Now I can state that DC is congruent to segment BC by CP, CT, C. Corresponding parts of congruent triangles are congruent. That verifies that if I have a point here, C, that is on the perpendicular bisector, then it is equidistant. And remember, equidistant has to be a perpendicular segment from this point to each side. Then that tells me that these two segments are going to be congruent. And that verifies theorem 5.4, the angle bisector theorem. On this slide, we're given that segment AC is the angle bisector of angle BAD. Then, point C, since it's on the angle bisector of the angle, must be equidistant from the sides of the angle. And the sides of the angle, we can start at the vertex, are AD and AB. Therefore, I know that there are segments that are congruent from point C as long as the segment from point C to the sides are perpendicular segments. And I have that with segment DC and segment BC. Since this part is true, I can then find the length of segment DC. These two segments are congruent, therefore 2x plus 5 equals 4x minus 17. Solving the equation, subtracting 2x on both sides, I get 2x minus 17 equals 5. Add 17 to both sides, I get 22 equals 2x. Therefore, x, when I divide by 2, is equal to 11. But they didn't ask us to find the value of x. We needed to find the value of x, but what they want us to do is to find the length of DC. Therefore, I just substitute into DC, which 2x plus 5, x is 11. And when I simplify, 22 plus 5 is 27. Therefore, DC is 27, and also BC is 27, since they are congruent. On this slide, we have a statement. Point E is equidistant to segment BA and segment BD. And if point E is equidistant to a sides of the angle, then point E must lie on the angle bisector. So point E is equidistant to segment BA and BD, then point E is on the angle bisector. Now they want us to name two congruent segments. Here I have segments from point E. I have EA and ED to the sides of the angle, and EC and EF to the sides of the angle. The only ones that we know that can be congruent are segments from that point on the angle bisector that are perpendicular to the sides. Therefore, segment EF is congruent to segment EC. I can't determine other lengths from E to the sides of the angle unless they are perpendicular to the sides of the angle.